All right, so a nucleus is held together by what force? Actually, there's two ways of thinking of this force. What's the first way? What's it called?
That glue stuff.
Gluons. Very good. Some people think of it as tiny little particles that glue the protons and neutrons together. Gluons. Some people don't believe that it's particles at all. They think it's a type of energy. Yes? The strong force. The strong force. The fact is that when atoms split apart, they don't need as much strong force. Or even when they're put together, when they're slammed together, the pieces have more mass than the original. So that mass has to go somewhere. We think that mass is being turned into energy. So there are two ways of liberating this strong force, or the gluons. They are fusion and fission. I need you to be able to distinguish between fission and fusion. And if I give you a reaction, you need to be able to look at it and go, oh, that's obviously fusion. Okay? Let's begin with fission.
In this video, we're going to talk about nuclear fission. Unstable radioactive nuclei, which occur naturally, sometimes emit strong radiation, especially in isotopes of uranium like uranium-238 or uranium-235. The disintegration converts the uranium isotope into stable lead, and in the process emits energy in the range of 1 to 5 mega-electron volts. That's 1 to 5 million electron volts, and even higher amounts of energy can be released by breaking unstable nuclei into even more parts. In 1939, a German scientist named Otto Hahn discovered that breaking up the nucleus of uranium-235 into two parts emits 200 million times the energy of the neutron which triggered it. He, along with his two colleagues, Lisa Meitner and Fritz Strassmann, found that when the nucleus of uranium-235 is bombarded with neutrons, it will absorb one of the neutrons. This results in an unstable compound nucleus, and the nucleus breaks into two equal parts. This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amounts of energy, is called nuclear fission. In the process, uranium-235 initially absorbs a slow-moving neutron, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction.
Here's the key thing you must remember. What started the reaction? A neutron. What is produced by the reaction?
A neutron.
Why is that important?
Because
So I have to start it, but at some point it will go on by itself. We call that a chain reaction.
During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. You should notice that a barium atom has 56 protons and a krypton atom has 36 protons, which add up to the uranium atom's 92 protons. The unstable uranium-236 nucleus also releases 3 neutrons in the process. This happens because barium-141 has 141 neutrons and krypton-92 has 92 neutrons, adding up to a total of 233 neutrons. To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equation of the nuclear fission reaction taking place can be represented by this equation. So as you can see from the equation, one neutron combines with uranium-235, forming an unstable compound nucleus, uranium-236. This unstable nucleus splits into 2 stable nuclei, barium-141 and krypton-92. In addition to these 2 nuclei, 3 neutrons are also emitted, as well as a high amount of energy, denoted in the equation by Q. Since uranium-236 emits 3 neutrons in the reaction, these neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amounts of energy being released by a single reaction.
Okay. Now, let's contrast that with
In this
nuclear
video,
fusion.
Nuclear fusion. In this video, we're going to understand how two or more nucleons merge or fuse together to create something more powerful and meaningful. So let's start by talking about the word nuclear fusion. Nuclear means the process which involves the nucleus, and fusion in English means two or more entities coming together or merging together to form one single entity. So, nuclear fusion can simply be defined as the fusion or combination of nuclei. Scientifically, nuclear fusion can be defined as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amounts of energy. For example, lighter nuclei such as lithium and helium, when combined together, form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is phrased in terms of energy release, which is usually very enormous rather than mass. Therefore, the law of conservation of energy is satisfied. Consider the example of two hydrogen nuclei combining to form deuterium. Here, one hydrogen atom combines with another hydrogen atom, giving deuterium, one positron and one neutrino. This deuterium, in turn, combines with another hydrogen nucleus to form a helium isotope. If two such helium isotopes are fused together, the formation of heavier helium takes place.
And this is why fusion is so attractive to us. Because it requires hydrogen, which we've got a ton of. Water has hydrogen in it. We're never going to run out of hydrogen. And it makes, as a waste product, what we put in our birthday balloons. On the other hand, nuclear fission, they gave you only two possibilities, krypton and barium. There's actually 35 different possibilities. There are 35 different very radioactive isotopes that are going to be produced from nuclear fission. Nuclear fission we can do. Nuclear fusion we can't. Not yet, anyway.
These three steps of the nuclear process, where four protons are fused together to form the heavier helium-4 nucleus and enormous amount of energy, is a nuclear fusion reaction. The chemical equation for this nuclear fusion is as follows. Four hydrogen nuclei, when fused together, give rise to the heavier helium. However, in spite of such a substantial amount of energy being released in the nuclear fusion reaction, there are no full-time nuclear reactors built so far for fusion reactions, as it is very hard to control such enormous energy release.
All right, so those are examples of fusion and fission. Yes?
How do we know if that's what it's going to do?
No, we can do it, but we have to spend $10 in order to get $1 out. Okay? We're hoping for the day that we can spend $5 in order to get $5. And then, hopefully, the technology will improve so we can spend $4 to get $6. At that point, we're getting more energy than the energy we're putting in. Yes?
I was going to comment that haven't we done fusion bombs?
Oh, yeah. I don't know about fusion bombs. We can do fusion. I'm not sure about fusion bombs. That might be a little bit science fiction-ish. Check. Combining two smallish nuclei to make a bigger one. Fission is splitting a larger nuclei into smaller ones. The earliest fission reaction that we played around with was bombarding uranium-235 with neutron to form barium and krypton. This was the first observable fission reaction. This started the whole process of Oak Ridge coming into existence. Here's the key thing. Using this reaction, you could make 2.1 times 10 to the 13 joules per mole of 235. Since the mass of 235 is 235, then that means per 235 grams. That's a lot of energy. That's about half a pound of 235 will give you, I think this is in the order of trillions of joules. Trillions of joules. Okay? Now consider how much coal you would have to burn in order to get 21 trillion. Okay, we're talking mountains and mountains. Mount Everest amount of coal. Is this the only type of fission reaction that happens? Herein is the problem. If barium and krypton were the only waste products here, then we could easily separate it because krypton is a gas and barium is not. But it doesn't always split into barium and krypton. It can actually split into any number of 35 different sets of daughter nuclei. So the waste that we produce in a nuclear reactor has to be stored very carefully and for millions of years. So one of the biggest problems with nuclear fission is the waste product. What is the key to every uranium reaction again? Neutrons. Why is that important? They start the reaction and they're produced by the reaction. That's right. So one neutron will split an atom, and 3 neutrons can now be used to split other atoms. What do we call it when neutrons that are produced can sustain the reaction without any new ones being added? Chain reaction. And what do we call? By the way, this is the 2 terms that you will find in the middle of your homework this evening. What do we call the minimum amount of energy of material needed to sustain a chain reaction? That is called critical mass. When you have enough fissionable uranium or plutonium that it can go off by itself and you don't need to keep adding neutrons, that's called critical mass. Critical mass. All right, so this is a chain reaction, and when you have enough of it that it can go off by itself, it's called critical mass. What did we call the U.S. secret project that explored these concepts during the latter end of the World War II? There's a shopping center down the road named after it, the Manhattan Project. All right, so how does a nuclear reactor work?
Nuclear power plants are thermal power stations which generate electrical energy from heat. They consist of numerous buildings and facilities, the most important of which are as follows. The turbine building houses several turbines as well as the generator necessary for electrical power generation. The containment building where the nuclear reactor is housed is made of meter-thick reinforced concrete. Inside this building, nuclear reactions take place where water is heated up. The cooling tower, which can be as tall as 200 meters, is where hot water is cooled. In order to easily understand the underlying principles, the following is a description of the most important components of a nuclear power plant that uses a pressurized water reactor, PWR. In the reactor pressure vessel, the nuclear reaction and the associated release of thermal energy takes place. In a pressurized water reactor, as in this case, the reactor pressure vessel stands about 12 meters tall. The walls are about 25 centimeters thick. Inside is where the fuel assemblies can be found. In pressurized water reactors, about 150 such assemblies are installed. A single fuel assembly is composed of many fuel rods.
Okay, so these are fuel rods. This is where they're going to put the uranium. And I wonder what happened. Is there a little cardboard? Yes. Oh, there it is. Okay. So inside these fuel rods, you're going to find these fuel pellets. These fuel pellets are made up of carbon-boron combination, I think. And this little fuel rod will have enough uranium to equal in energy to 3 barrels of oil, 1 ton of coal, and 17,000 cubic feet of natural gas in this little pellet right here. So these fuel rods are going to be full of those little pellets, and that's where the enriched uranium. Now, listen very carefully. What they mean by, when we think of something that's enriched, that means there's a lot of it in there. What they call enriched is 3% uranium-235, 97% 238. The reason why that's considered enriched is because normally it's 99.99% uranium-235, 0.001% 238, and 0.001% 235. So when you go from 0.001 to 3%, that's pretty rich, if you think about it. Now, what's the significance of 3%? Well, I need to give you another percentage. At 15%, you have enough mass for there to be a nuclear explosion. So, can a nuclear reactor ever have enough uranium to explode like a nuclear bomb? No.
A fuel rod is about 5 meters in length and has a diameter of about 23 centimeters. The actual nuclear fuel is found inside of each fuel rod. Small nuclear fuel pellets composed of enriched uranium or plutonium make nuclear fission chain reaction possible. In the fission chain reaction, thermal energy is released.
Okay, so here they're going to blast these fuel rods with neutrons, causing the uranium to split. And every time it splits, it gives off a little bit of energy. So when you have millions and millions of these guys splitting every second, it gives off a lot of energy. So much energy that it's able to melt these fuel assemblies down. It's called a meltdown. You're going to have to cool it down. And actually, you can't really just let it go off by itself. So these rods up here, they're called control rods. And what they do is when they lower these control rods down in between the fuel assemblies, the control rods are made up of very dense materials that suck up neutrons and don't let them go anywhere. So without neutrons, what happens to our chain reaction? So by inserting these control rods in there, you can stop the whole thing and let it cool down. If it's running too hot, you bring in a few control rods. Let it slow down a little bit. You want to open it up, bring up the control rods, let them have their fun. Okay? So, it's still going to get really, really hot. So you're going to have to cool it down. What material do you know of that has a very high specific heat that is great for cooling things down? And that's what cools down this reaction vessel.
Water is needed in order to absorb the thermal energy and keep the chain reaction going. Inside the vessel, the water is heated to over 570 degrees Fahrenheit.
Okay, what's the problem with heating water up to 570 degrees Fahrenheit? Okay, it's going to boil at 212. It's going to turn into steam. You allow the super hot energy, the fuel containment vessels to be exposed to air by letting the water boil away, and it will melt down. You cannot allow this water to boil. So they're going to pressurize it. They're going to pump it to such a degree that it can no longer boil at 100 degrees Celsius. It'll have to boil much higher than 100. Okay, so this water is not allowed to boil. That's what you need to remember.
The water does not boil, however, since the pressurizer maintains the water pressure constant at around 160 bars. The heated water is eventually pumped to a heat exchanger, also called steam generator.
Okay, so it is pumped into these little copper coils. As these fuel pellets do their thing, some of them crack open, allowing the radioactive waste to get out and into the water. This water is now dangerous water. It is highly radioactive, but it stays within a loop. It needs to be cooled down because you don't want it to boil. Boiling is bad. So it is brought up into these loops, and you're going to have some way of cooling down that copper, or else the copper will melt. What's the best way you can use? What's a chemical that you can use that's really good for absorbing heat and carrying it away? Water! Wow! Okay, so surrounding this copper coil and never actually in contact with it is a different water. This water is not under pressure. This water is allowed to become steam.
These are typically in the form of a shell and tube heat exchanger. Hot water flows through the U-tubes, heating up the metal of the pipes so that any water inside the heat exchanger begins to boil.
Okay, so it's capturing all that energy and beginning to turn into steam. Now, why do we want it to turn into steam? Because we need the steam to do the
The
work.
resulting steam is eventually fed through a set of pipes to the turbine building.
Okay, so here comes the steam, and it's going to make this big giant flywheel spinning. The steam will continue on and cause these flywheels to spin. They're called turbines. They cause this big giant electromagnet to spin in place. There are hundreds and hundreds of pounds of copper wire surrounding this. I don't know if you ever played around with an electromagnet when you were in middle school, but Sasquatch, what happens when you take an electromagnet and have it spin in place surrounded by copper wire? Electricity is formed. Do we know why? No. We just know it does. So this is a big giant 2-story electromagnet that creates a lot of electricity. And what's causing the electromagnet to spin? The steam.
The steam first drives a high-pressure turbine and then is typically fed to 2 low-pressure turbines. All of the turbines are connected by a spinning shaft to the electrical generator, which in turn produces AC electricity from the shaft's rotational energy.
Now, the steam has lost a lot of energy, and some of it has condensed, but a lot of it hasn't. It needs to make its way back to the other section, and when it comes back, it needs to be nice, cool water. So you're going to have to cool this water down. So you're going to have to send it through another loop.
The steam is converted again into liquid form in a condenser, and then returned back to the steam generator.
So that
The
it can do
water
its thing
needed for
again.
this often comes from an adjacent river, or is cooled in a cooling tower. The water circulation systems are always kept separate from one another. Water in the primary circulation system never leaves the containment building.
Okay, so this is called the primary circuit. And that water is very dangerous. And after the reactor is shut down for maintenance, that water has to be stored as radioactive waste. That water is very dangerous, but it never comes in contact with anything else. It stays in this little loop. Here, the energy that's picked up here is going to be transferred to this secondary loop.
This water is radioactive, since it has been in direct contact with the fuel rods. Water in the secondary circulation system is used to drive the turbine.
So this is the water that does the work for us, that makes electricity. Yay! We've made electricity. But this water needs to come back here and do its job again. So it needs to cool down.
and is not radioactive. The cooling circulation system provides cool water.
The third circuit is what's going, the warm water is going to be pumped up here, this big giant cooling tower. When we think of nuclear reactor, we think of this thing, don't we? It's 10 stories tall. It's huge. Okay? Its job is to cool down that water so that it can be sent back over here in order to cool down the secondary loop, in order to do work for us, so it can be sent back here in order to cool down the primary loop. So we're taking energy from here and making it work for us, and then finally cooling it down here.
And is used to condense the steam in the secondary.
Any questions? Yes?
Why is there a high pressure turbine and then two low pressure? Why not?
I'm not sure. That's physics. It's more efficient that way. I have no idea why. Yes?
This sounds like a really complicated process. How exactly, or how many times did we create this and it not work?
There's been, amazingly enough, we've had a huge success rate. There's various different forms of this thing, and there have only been 3 accidents. Of course, 2 of those 3 have been really, really bad. This is one of those things that we don't hear about the thousands and thousands of hours, the hundreds of reactors that work perfectly and provide cheap electricity for everyone. We don't hear about that. We hear about Fukushima and Chernobyl. Cooling tower. This is a cool, cool place. We got to tour the cooling tower back before Watts Bar came online. Now, you tell me why they told us, because we were going to actually walk into the cooling tower. They told us not to let the girls wear any dresses.
It tends to be like that in Maryland.
Cooling towers are commonly part of thermal power stations and are the most recognizable feature of a nuclear power plant. Cooling towers are shell structures built of concrete in which hot water is allowed to cool. Thereby, thermal energy is released to the environment. The most well-known form is the natural draft wet cooling tower, as shown in this animation. Natural draft wet cooling towers can be up to 200 meters tall and are made up of a cold water basin.
Okay, the structure is actually sitting on stilts. So this is open to the air, and the whole structure is sitting on this ring of pylons. Its job is to allow air to come in from underneath. There is a floor here that's made of this grating material. That's where we were allowed to go and walk on. And folks, the whole thing is designed to suck up air through it, because what they're trying to do is bring in the hot water from the tertiary loop and to let it, and they just sprinkle, like sprinkle systems. It's sprinkling down upon this as cool air comes up. So as the air comes up, the water comes down, the water cools down here, and it's pumped back into the reactor. Okay? What happened to us once, what did we experience when we got over here? Yes, an incredible amount of wind coming up from the bottom. So if you had a skirt on, you've seen that Marilyn Monroe video, right?
An air inlet near the bottom of the tower, spray nozzles, and a drift eliminator. Other elements, such as towel packings, are also commonly used in order to increase efficiency. For clarity, however, these are not described here. Hot water is pumped to the spray nozzles. Natural convection draws cold air in from outside. The cold air cools the water. During this process, about 2% of the water evaporates. This can be seen as plumes of steam. Natural draft wet cooling towers function according to the simple principle of the stag effect, also known as natural circulation. Since warm air is less dense than cold air, warm air rises due to buoyancy and escapes out.
So warm air rises, and it has to be replaced by something, so cool air from outside rushes in and cools it off. Yes?
Are you wasting all that steam that comes out?
Yeah, some of it is wasted. Yeah, can't help it. Okay, so what happened? What is the critical part of any nuclear reactor?
The reactor.
Water.
Haven't heard it yet.
Steam, the fuel pellet.
The people that work there.
Folks, if you can't pump water through, what happens?
It's gonna blow up and kill you.
So in 3 Mile Island and in Chernobyl, human errors caused the pumps here to be shut down. Without the pumps, the water here turned into steam. Once it turned into steam, it started cracking open the containment vessel, allowing air to come in. Once you allow air to come in, this thing melts down. So it forms what is called corium down here. It actually melts down, and in the 3 Mile Island, it worked perfectly in that it was not able to breach the basement. Yes?
It doesn't sound like a very sudden process. Does it just kind of like melt and then it's done? Or there's no explosion or anything?
Oh no, there's going to be an explosion because once this metal, it reacts with oxygen to form hydrogen gas. In Chernobyl, the hydrogen gas built up, reacted with oxygen, blew the top off that building. They found parts of the roof several miles away. Okay, this thing melted down, breached the sub-basement, got into the soil and the rock beneath. Terrible, terrible. 3 Mile Island, the whole thing was contained, and steam, just a little bit of radioactive steam got out. That's it. So it's considered a successful failure. Now, what happened in Fukushima was the reactor was designed to withstand an earthquake, and it did. Great job, awesome. As soon as the earthquake occurred, the control rods were lowered, the reactor was shut down, and it started to cool off. The electricity blinked off. That's okay. They had diesel-fueled generators that kept the pumps going. Yay, we're doing great. And then what happened after the earthquake?
Pump shut off.
Why did the pumps shut off?
Human error.
Tsunami.
Oh, yeah.
The tsunami came in, flooded the storage facilities where the generators were, stopped the generators, the pumps stopped, and the rest is all 4 reactors melted down, releasing
Turn it off.
on what?
Can't you just like, couldn't they just like
They
turn it
did, but
off?
this is still 500 degrees, my friend.
Oh, okay.
Okay, I mean, yes, they shut it down, but still, it was so hot that it still melted down.
They should have just started spraying.
It would have been okay if the pump was allowed to keep on working.
Oh.
Yes, Marie.
Does that mean all the radioactive materials got into the water?
Got into the ocean.
So basically that whole section of the ocean is radioactive.
Well, no, it's spread. So, yeah, it's okay because by now it's in San Francisco as well.
It's like as radioactive as bananas.
Why can a nuclear reactor not explode like a nuclear reaction?
Because they ain't got enough of that 1 year.
Not enough 235. Here is the core. And we talked about a meltdown. A breeder reactor. In a breeder reactor, see, this is normal. Breeder reactor uses uranium-238 to produce neptunium. And then neptunium produces plutonium by beta decay. What's so special about that? Plutonium is the other fissionable material. So if you have a nuclear reactor and it's designed as a breeder reactor, you also have the ability to make plutonium. That's why K-25 doesn't work anymore. We don't need it because our own reactors make what we need for nuclear weapons. That is also why the Iranians, even though they keep saying, oh, we're not interested in making nuclear weapons, really, we're just concerned about global warming. And we would like to make a nuclear reactor so that we have green energy and we won't hurt the environment. Okay, if they have a reactor, what will they have within a couple of years? Nuclear weapons. Yes, Max.
So Y12 is a big deposit of grade uranium, right? And that's like 90% 235. So can they like?
No, there's no 90% 235. 15% 235.
So if they convert that into like reactor, does that mean they get more out of it?
Hey, hush. Go, Max.
Does that mean they can make like 5 times the reactor grade uranium if they like add 238 into it by breaking down the stuff?
I'm not sure how it works. I can see that it's conceivable, yeah. Okay, so what's the problem with nuclear fission? What are you going to do with the nuclear waste? Plutonium is very toxic.
You're going to store it in a water.
So you bring it to Oak Ridge and store it here. All right, we'll have to finish